Okay, so welcome to this particular class where we'll be looking at the 2025 January final exam for P192. And to begin with, I'm just going to show you there are those who like panicking about formulas or mastering some formulas that you feel are tough and stuff. Remember to say the formulas are some of the formulas are provided for. So we'll be provided with some of these on the first page for the formula sheet. Then here we've been given physical constants like that. So this is what you are going to be given on the cover page of your exam. So look at the entire paper for 2025 January exam or final January exam for physics, your introductory physics, until we are done. So without wasting much time, let's go to the multiple choice questions or the multiple choice part, which is part A or section A from question 1 to question 10. And question 1 reads, water in a tank is increased in temperature from 25 degrees Celsius to 58 degrees Celsius. The water volume increases by 0.30 liters. Find the volume of the water before the temperature increase. Use the value of 2.14 times 10 to the power minus 4 degrees Celsius for the volume coefficient of expansion of water. So this should have been to the power minus 1. Huh? The coefficient is per degree Celsius and not just a degree Celsius like that. All right, so this is a multiple choice question, but as we all know, the basic concept is about thermal expansion. In this particular case, we are dealing with volume expansion. So the general formula for calculating change in volume, we say change in volume is equal to the coefficient of volume expansion, which is represented by beta, multiplied by the initial volume, multiplied by the change in temperature like that. So they've already given us the change in volume. They've given us the coefficient of volume expansion. They've given us the change in temperature to say we are starting with 25 degrees Celsius to 58 degrees Celsius. So they are looking for the initial volume. Or is it? Find the volume of the water before the temperature increase, which means we are looking for the initial volume in this particular case. So we are just going to make our initial volume the subject to the formula. So I'll divide both sides of my equation by beta multiplied by the change in temperature. Even that side, beta multiplied by the change in temperature like that. This is going to cancel out on the right-hand side of my equation. Hence, my initial volume will be equal to the change in volume divided by beta multiplied by the change in temperature in this particular case. So we've already been given the volume in liters. We have our coefficient of volume expansion. Then we also have our change in temperature, which when we talk about change in temperature, we know to say this is just basically T final minus T initial like that, which is 58 minus 25 like this. 58 minus 25, and this is going to give me a temperature increase or a temperature change of 33 degrees Celsius. And this is what I'm going to plug into my equation. Hence, my initial velocity will be equal to the change in volume, which we have already been given, 0.30, divided by the coefficient of volume expansion, which is 2.14 times 10 to the power minus 4. Put it in brackets like that, multiplied by the change in temperature, which is has been calculated to be 33. All right, so multiply the denominator. We have 0.30 at the top. Then we have 2.14 times 10 to the power minus 4 multiplied by 33. This is giving me 0.007062, like this. All right, so now I'm only going to divide. And this is giving me my temperature, or rather my initial volume, to be equal to 42.5. 42.5 liters. So my initial volume is equal to 42.5 liters, which is equal to option C. This is equal to option C. So option C is the correct answer for question 1. Let's quickly move on to question 2. And question 2 is saying if change in Q stands for the amount of heat absorbed or released by a substance of mass m when it undergoes a temperature change over delta T, then change in Q over mass multiplied by delta T is equal to dash. If change in Q stands for amount of heat absorbed or released by a substance of mass m when it undergoes a temperature change delta T, then the change the change in Q over m delta T is equal to dash. All right, so this formula is basically talking about uh, temperature that is absorbed, or the amount of thermal energy that is absorbed by a substance of a given mass when there's change in temperature. So that's the basic concept. So we have to remember the standard formula for calculating thermal energy that is absorbed when there is change in temperature of a particular substance, or of a particular substance which has a given mass. We say change in Q, is equal to mass multiplied by specific heat capacity multiplied by change in temperature. This is the formula that we use for heat that is absorbed or released when there is a certain change in temperature. So if this is what we have this as our heat absorbed or released, we have this as our mass of a substance, then we have this as the specific heat capacity, then we have this as your change in temperature. So what are they saying? They are saying what is change in Q divided by M multiplied by change in T going to give. So we're going to do just that. We're dividing change in Q by mass multiplied by delta T. Even that side, I'm going to multiply it by mass multiplied by delta T like this. So mass and mass is going to cancel out, whilst delta T and delta T is going to cancel out. That means I'm going to have my specific heat capacity being equal to delta Q over mass multiplied by delta T. So this is what I'm going to have, meaning my delta Q divided by mass multiplied by delta T will just be equal to specific heat capacity. So this is giving us a specific heat capacity, which is option C like that. All right, so that is all about question 2. Question 3 is saying a thermodynamic system which heat does not escape the system is called the dash. A thermodynamic system, so this is just a conceptual question. They want you to understand a thermodynamic system that has no heat escaping the system. So if the heat is not escaping the system or entering the system, that means there is no change in heat to that particular system. And once this particular scenario, what are we going to have? This is very simple. This is very, very simple. So we have no heat escaping the system. That means our Q is equal to what? Our Q is equal to 0, like that. Therefore, if our Q is equal to 0, which means this process is going to be an adiabatic process. To be an adiabatic process, because an adiabatic process, that's a process where you have no heat escaping the system, no heat is entering the system. So there's okay, so the correct option is option B. Isothermal just basically means the process is taking place at a constant temperature. There is a constant temperature. Here we are talking about the heat. There's no addition of heat, which means there's no heat that is escaping the system. All right. So they've also talked about isovolumetric, which means the volume is constant. Isobaric, that means there is constant pressure. An isobaric process means the process is taking place at a constant pressure. Question 4 is saying two charges, Q1 and Q2, are placed d meters apart. If the distance d is halved, what is the repulsive force between them. If the distance d is halved, which means we are reducing the distance between the two charges, what's going to happen to the repulsive force between them? All right, so this question is basically talking about Coulomb's law. And I will not say the force between two charges using Coulomb's law is equal to K, which is the Coulomb's constant, multiplied by the charges, which in this particular case will be Q1 and Q2, divided by the square of the distance between the two charges, like that. So this is what we have. And you're going to notice to say, from this equation, the distance or the square of the distance here is inversely proportional to the repulsive force that is between them. So we're going to say repulsive force will be equal to what? It will be equal to, or rather, I want to establish a relationship, not will be inversely proportional to 1 over d squared, like this, which means as you increase the square of d, the force is going to reduce. Or still, as you reduce the square of d, the repulsive force is going to do what? Is going to increase. So they've told us to say the distance has been halved, which means initially we had d, and now we have what? We have d over 2, like this. This is what we have. That's why we are saying the distance has been what? The distance has been halved. All right. So if this was our initial repulsive force, let's assume this is our initial repulsive force. Now, in the next relationship, I'm going to plug where there's d squared, I'll put this value. Where there's d, I'll put this value. So I'll say my F will be equal to the constant K, Q1, Q2 divided by d over 2. And this is squared like this. All right. So I'll have my K, Q1, Q2 being equal to d squared over 2 squared, of which 2 squared will just basically give us 4. All right. So this is what we're having. That means our repulsive force will be equal to what? This is the same. I have, okay, let me write this one like this. So this is the same as I have my Q. Rub here a bit. Okay, I have my K here. K being multiplied to these two guys that we have here. So whenever we have a ratio like this, I remember during your secondary school days, if you have maybe we say 1 or A over B, then this is over C like that. You know, to say this just basically implies that this denominator multiplied by the numerator divided by what is it in the middle there. So we're going to do the same with this one. So we'll say 4 multiplied by the numerator, which is K multiplied by Q1, Q2. So I'm going to have my repulsive force being equal to 4K Q1, Q2 over D squared, like that. So I'll factorize out the 4, or I'll put the 4 outside the brackets. That means our force, our apparent force when the distance is halved, will be equal to 4K Q1, Q2 divided by D squared, like this. All right. So that means apparently our new repulsive force when the distance is halved is going to be equal to what? It's going to be equal to 4 times the initial repulsive force that we had here. So that basically means our correct answer here is in option B. Our correct answer here is option B for like that. All right, we move on to question 5. Question 5 is saying, or this is also a conceptual question. It's saying the electrostatic force acting per unit positive test charge at a location is a measure of dash. The electrostatic force acting on a, what do they say? The electrostatic force acting per unit positive test charge at a location is a measure of dash. Okay, so this is just testing you on the concept of the electrostatic force itself, and we have to now recall our knowledge about electric field and stuff. So How do we define the electric field? Because here they're talking, they're telling us about an electrostatic force. They're saying the electrostatic force acting per unit positive test charge at a location is a measure of, and if you remember, we say the electric field strength. The definition of electric field strength, mathematically, we say this is equal to what? This is equal to force, which is the electric force itself, divided by Q, of which Q is a test charge. So they've already talked about a test charge here. This is the electrostatic force here. So they're saying the electrostatic force per. So this is all giving us the formula for what? For electric field. This is electric field because electric field is the measure of an electrostatic force that is acting on a charge. So as simple as that. So our final answer here is electric field, B. And we know to say electric field is equal to the electrostatic force itself divided by that charge there. All right, so that's question 5. Question 6. Which description of Kirchhoff's first law is correct? Which description of Kirchhoff's first law is correct? So remember, Kirchhoff's first law talks about current. It's also known as the Kirchhoff's current law. So it considers the current at the junction in a circuit and its consequence on the conservation of charge. It considers the current at the junction in a circuit and its consequence on the energy of and its consequence on the conservation of energy. It considers the electromotive force and potential difference in a circuit loop and is a consequence of the conservation of charge. D, it considers the electromotive forces and potential difference in a circuit loop and is a consequence of the conservation of energy. And E, none of the above. All right, so I've just mentioned to say the Kirchhoff's first law is also known as the Kirchhoff's current law, or rather KCL. And what is the principle behind Kirchhoff's first law? We know it says this, it talks about current at the junction. It says at the junction, the total current that is entering that particular junction should be equal to the total current that is leaving that particular junction. And this statement is directly coming from where? It's coming from the conservation of charge. So we say the summation of current that is entering should be equal to the summation of current that is coming out like this. This is Kirchhoff's current law. So it's talking about current at a junction. That's the first thing you should notice. And it is being based on what? On conservation of charge. On conservation of what? Conservation of charge, which means from the options that we've been given here, option considers the current at the junction and the consequence of the conservation of charge, which means option A is the correct answer. Option A is the correct answer in this particular case. All right. Let's move on to the next question. We have question 7. Question 7 is saying a circuit is set up as shown in the diagram. A circuit is set up as shown in the diagram. So we have this particular circuit where we have EMF in the battery of 9 volts. Then we have these two resistors that are in series. So it's saying the potential difference across the 40 ohms resistor is dash. The potential difference, which means the voltage across the 40 ohms resistor is equal to dash. All right, so here we're just basically going to apply our knowledge when it comes to resistors in series, but also resistors in parallel, because they want us to find the voltage, the potential difference in the 40 ohms resistor, which is this particular resistor that we have here. And if you look at the orientation of our resistors, we're going to find that they are oriented in series, or they've been arranged in series with each other. So When a circuit is in series like this, what does it state about total resistance? What does it state about total current? And what does it state about um, voltage distribution? Those are the things that you're supposed to remember. So in a series circuit like this one, you're supposed to remember that the current is actually the same in all the resistors, whilst the voltage divides according to the resistance, which means when you have resistors or the voltage that are or resistors that are in series, the total voltage will be equal to the summation of the voltage that is here plus the voltage that is there. Whilst if it was current, current is going to be similar. Whilst the opposite is the case when it comes to resistors that are parallel to each other. You're going to find that the voltage in the resistors that are parallel is going to be similar in across all the resistors, or still the current will be equal to the individual or the summation of the individual currents that are passing through those particular resistors that are what? That are arranged in or rather that are parallel to each other. As simple as that. So the first thing that we're going to do here is find the total resistance, and you know to say R total in series. RT in series is just equal to the individual sums or the sum of the resistors that we've been given. Within this particular case, it will be R1 plus R2. So this will be equal to 80 plus 40 ohms. Hence, my total resistance will be equal to 100 and the total ohms like this. Then after this, let's do what? Let's find the current. So we're going to use Ohm's law to find current, and you know to say using Ohm's law, voltage is equal to current multiplied by resistance. Voltage is equal to current multiplied by resistance. We're looking for current, so divide both sides by resistance. This will be, I've calculated resistance here. So that means my current will be equal to voltage, which is 9 volts in this particular case, divided by resistance, which is 120. So our current here, let me just plug this in. Our current here will be equal to 0.075 amps. 0.075 amps. Now that we've calculated the current, we know to say this is the same current that is passing through both resistors. Since in series, the current is similar everywhere. So this is the current that is passing through all the resistors. Now, we can use Ohm's law again. Voltage is equal to current multiplied by resistance to find the voltage of each resistor that we have here. So they've told us to say we should calculate this one that we have there. So we're going to say the voltage here will be equal to the current, which is 0.075 multiplied by the resistance, which is 40. As simple as that. That means the voltage passing through this resistor is going to be equal to 3 volts. As simple as that. So these are the steps that we're supposed to follow. That means our correct answer in this particular case is option B. Question 8 is saying, what is the unit for electric current? What is the unit for electric current? And we all know, I've been mentioning about it to say the unit of measurement for electric current is actually the ampere, which is option C here, which is the option C in this particular case. All right. Question 9 is saying, what is the value of capacitance of a capacitor which has a voltage of 4 volts and has 16 coulombs of charge? What is the value of capacitance of a capacitor which has a voltage of 4 volts and has 16 coulombs of charge? All right, so this is a question about capacitance. And uh, using the principles of capacitance, we know, say, if we want to find the charge on capacitance, what do we say? Say Q is equal to current multiplied by the voltage, like that. Q is equal to capacitance, or rather, not current, sorry. This is capacitance. When I see C, I'm used to saying current. So this is capacitance. So charge is equal to capacitance multiplied by voltage. This is the formula that we use. So Using what we've been given in question 9, you can tell to say we've been given voltage and we've been given what? We've been given a capacitance. So they want us to find what? What is the value of capacitance of a capacitor that has a voltage of this and has this 16 coulombs of charge. So they've given us charge. This is charge and this is voltage. So we are looking for capacitance. So divide both sides by voltage. That means capacitance will be equal to Q divided by V. So our Q is 16 coulombs divided by our voltage, which is 4 volts. That means my capacitance will just basically be equal to 4 farad. Our capacitance will be equal to 4 farads, which is option B. So option B is the correct answer. Question 10 is saying, what is meant by the half-life of a radioactive isotope? So this is also another conceptual question. They're asking about half-life, T-half. What is meant by the half-life of a radioactive isotope? And option A is saying half of the time taken for all the original nuclei to decay. B, the time taken for half of the original nuclei to decay. C, the time taken for the charge on all the nuclei to halve. D, the time taken for the mass of each nuclei to halve. D, the time taken for the original nucleus to increase by half. All right, so when we're talking about half-life, by definition, we are not talking about the increase. We are basically talking about the time itself. We're actually talking about the time itself. So what is meant by half-life? What's the principle behind half-life? So when we talk about half-life, we are basically talking about the time that is required for half of the unstable radioactive nuclei in a given sample to undergo radioactive decay. So it's going, or it's emitting radioactive particles, which we call radioactive decay, to become a stable compound, a stable isotope. So in this particular case, we are looking at the time that is required for half of the original quantity of the radioactive isotope that you have to decay away into um, a stable isotope. That is the concept, or the whole concept behind the half-life, but also radioactive decay. So looking at the options that we've been given, it's the time taken for half of the original nuclei to decay. It's the time taken for half the original nuclei to decay. That means for question 10, the correct option, or the correct answer, is option B. It's the time taken for half of the original nuclei to decay. Hence, we call it T half. All right, so here we found 4, here we found ampere, here we found 3, like that. So this is it about section A, which contained only multiple choice questions. This is it about section A, which only contained the multiple choice questions. As simple as that. Let's move on to section B. Section B, question 1 is saying a substance is heated at a constant rate and its temperature is taken every minute. During the heating, the substance undergoes the change of state. The results are shown on the graph below. The results are shown on the graph below. So we have the temperature time graph here. We have temperature on the y-axis, but also time on the x-axis. So the temperature is changing as the time is also changing here. So they want us to, in part 1, state and define the type of heat energy on section BC shown on the graph. State and define the type of heat energy on section BC. So where is section BC? Section BC is here, and we can tell to say on section BC, the temperature is constant. On section BC, the temperature is constant. So they want us to mention this temperature or to mention this energy, but also defining this particular energy. So this is at its melting point. We can tell to say this is at the melting point, and at the melting point, there is a constant temperature. Why is the temperature not changing? Remember using or when we're learning about melting of substances to say the temperature is going to remain constant because the heat energy is absorbed to break down the bonds that existed in the solid or the solid form of the sample that you are dealing with to melt it into a liquid. So melting is taking place. So the energy, the reason we're not experiencing a change in temperature is because the thermal energy, the heat that is being added to the system is absorbed, and it is being absorbed to break down the bonds that existed in the solid. Hence, the substance changing from solid to liquid at a constant temperature. If it's water, we all know to say that happens at 0 degrees Celsius. So they want us to state the type of uh, heat energy on section BC. So what type of heat energy? It's the energy that is breaking down the bonds on the solid to turn it into a liquid. And what's the name that we give this energy? We call it the latent heat of fusion. So part one, this is latent heat of fusion. The definition of latent heat of fusion, I've already mentioned, is the heat that is required to change the substance from a solid to a liquid without the change in temperature, without the change in temperature. So it's the thermal energy, heat energy required to change state of a substance from solid to liquid at a constant temperature. All right, so this is the definition of latent heat of fusion, and this is part one of our question. If our graph was extended here, you're going to notice to say we're going to have another latent heat here, but this latent heat is now the heat energy that is required to change the the state of this particular substance from a liquid to a gas. And this is also taking place at 100 degrees, or rather at a constant temperature, not 100 degrees. If it's water, it's going to take place at the boiling point of water, which is 100 degrees Celsius. As simple as that. So that is about part one. Part two is saying explain why the temperature is not changing between B and C on the graph. So I've already explained this part. The reason it's not changing is because the heat energy that is being supplied here is used to do what? To break down the intermolecular forces using during melting. So I'll just say because the heat, the Q, is absorbed to break break down down break down the intermolecular forces between the molecules like this. So This thermal energy is used to break down the bonds rather than it increasing the temperature of the substance or increasing the kinetic energy of a substance. So this is the explanation that you are required to indicate here. And this is part A of question 1. Part B is saying an oxygen molecule has a molecular mass of 32 grams per mole. An oxygen molecule has a molecular mass of 32 grams per mole. Given that at a certain absolute temperature, its mean square speed is 514 meters per second, calculate the value of the absolute temperature. So they've given us a Boltzmann constant here, but also the universal gas constant here. So we now want to do what? We now want to calculate the temperature. They want us to calculate the value of the absolute temperature. All right. So what are we supposed to remember here? The basic concept here is about uh, root mean square speed. So we're going to first establish the relationship between the root mean square speed, then we will express it in terms of what? In terms of absolute temperature, which is T. So we know to say the value of root mean square speed is calculated by 3RT divided by M, like this. So we have the molar mass here, the absolute temperature, the universal gas constant, and the root mean square speed itself. What are we looking for? We are looking for the value of the absolute temperature there, which means I'm supposed to make my absolute temperature the subject of the formula. How am I going to do that? We can start first by raising both sides of our equation to a square so that we take away or we do away with the square root sign that we have here. That means I'm going to have my 3RT over molar mass being equal to VRMS squared, like this. This is what we're having. From here, we can multiply everything with the reciprocal of what we want to do away with, which means I'll just multiply this by the value of M over 3R. Even here, the same. Anyway, let me just say everything on both sides of my equation. So that means I'm going to have T on the left-hand side being equal to V RMS squared multiplied by M over 3R. Okay, I hope this is making sense. This is what we are having when we make our T the subject to the formula. Then from here, we can just plug in what we are looking for because they've already been given in their SI units. So we've been given the root mean square speed itself. We've been given the molar mass. We've been given the universal gas constant. So I'm just going to plug in what I've been given. My absolute temperature will be equal to 514 squared multiplied by the molar mass, which is 0.032, 0.032 divided by 3 multiplied by the universal gas constant, which have been given to be 8.314 joules per kilo mole. All right, so we have kilo mole here. That's why even these grams per, where is it? Grams per mole have to be turned into kilo mole. So if you divide them by 1,000, that's why we're getting the 0.03 that we have here. All right, as simple as that. So this is going to be equal to what? Let me just multiply what I have. So 0.032 multiplied by 514 squared multiplied by 514 squared. This is giving me 8454, 8454.272 like this over 3 multiplied by 8.314. This is giving me 24.942. All right, like this. If I divide this, I'm getting an absolute temperature my T, you can just write it at the top. My absolute temperature T will be equal to 338.96 Kelvin. 338.96 Kelvin. All right, so we've been given everything here. Kelvin is going to be our subject of the formula. Kelvin is going to be equal to the subject of the formula. So what are we supposed to do? Make sure to say your gram that is here is converted to kilograms. That's why we divide this by 100, and we're going to get what? We're going to get 0.032 kgs per mole. Then our universal gas constant has already been given in its SI units, 8.314 joules per Kelvin mole here, not kilomole. This is Kelvin mole. Then we have our Boltzmann constant, which in this particular case we did not use because we used the formula that does not involve the Boltzmann constant. There are two formulas that are used to calculate the root mean square speed. The other one involves the Boltzmann constant, whilst the other one does not. So in this particular case, we've used the one that does not. Hence, we are getting an answer which is equal to 338.96 Kelvin. Let's look at part C. Part C is saying a beaker contains 0.25 kgs of water at room temperature. The beaker of water is heated until the water reaches boiling point, which is 100 degrees Celsius. The specific capacity of water is 4200 joules per kg degree Celsius. The total amount of thermal energy supplied to the water is 84,000 joules. Calculate the temperature of the water before it was heated. Calculate the temperature of the water before it's heated. All right, so we are also talking about temperature, mass, specific capacity, which means the whole concept behind this question is what is it? Specific capacity. So we know to say using specific capacity, we say Q is equal to mass multiplied by specific capacity multiplied by change in temperature multiplied by change in temperature, like this. This is the relationship between heat absorbed and the change in temperature and mass, but also specific capacity. So they want us to do what? They want us to calculate the temperature of water before it was heated. All right, so they've given us the mass to be 0.25 kilograms. They've given us the specific capacity to be 4200 joules per kg degree Celsius. They've given us what else? They've given us Q absorbed to say this is 84,000 joules, like this. All right, and if this is what we have, what are we going to do? We know to say change in temperature just basically means T final minus T initial, like this. So what are we looking for? We are looking for the T initial here. So the first things first, let's use this same equation that I have at the top here to find the change in temperature. And once I calculate the change in temperature, remember I've already been given what? I've already been given the final temperature. So I'll plug it into this particular formula to calculate the T initial. So my Q, which is 84,000, will be equal to mass, which is 0.25, 0.25 multiplied by specific capacity, which is 4200, multiplied by delta T, which is the change in temperature. Okay, so let me just punch this into my calculator. 0.25 multiplied by 4200 is giving me 1050. So my 84,000 will be equal to 1050 delta T, like that. Divide both sides by 1050, even that side by 1050. That's going to cancel out. That means my delta T will be equal to 8,400 divided by 105. This is giving me a change in temperature, which is equal to 80 degrees Celsius. Okay, so this is equal to 80 degrees Celsius. like that. And I'll get this value now and plug it into this particular formula since we've already gotten, or we've already been given the final temperature, which is equal to 100 degrees Celsius. So I'm going to say my delta T will be equal to T final, which is 100 degrees Celsius, minus the T initial that we are looking for. So our change in T is 80 degrees Celsius. This will be equal to 100 degrees Celsius minus T initial. All right, so I'll take this, since I don't want to be negative, to that side of my equation. Then I'll take this to that side of my equation. Hence, I'm going to have my T initial being equal to 100 degrees Celsius minus 80 degrees Celsius. That means my initial temperature is equal to 20 degrees Celsius. As simple as that. So that is the end of question 1, or section B, question 1. We finish off with the specific heat capacity of this particular substance, and we're calculating initial temperature. So we have calculated the initial temperature, and that ends there. Just follow those few steps in order for you to be able to calculate the initial temperature. So thank you very much for watching this particular video. Kindly remember to subscribe to the channel, like the video, but also share this particular video. Remember to register with us at discretelearning.com to find the full solutions to this past paper and more, including all the tutorial sheets already solved, quiz revisions, test revisions, and live classes, or classes on each and every topic that you are going to cover in your exam. So thank you very much for watching this particular video. See you next time.